Welcome back. Today we're going to talk about part of the most important result of this class. So there's something called the fundamental theorem of calculus. The fundamental theorem of calculus is the monumental result of a first semester calculus class. Okay. Now the thing is, that's usually the result is usually broken down into two separate parts, called the first fundamental theorem of calculus and the second fundamental theorem of calculus, or part 1 and part 2. Now you might ask me, well, professor, why in the world are you doing the second fundamental theorem of calculus first? Well, here's the thing. Usually textbooks do the first and second. Sometimes they do them together, and it's a really long section. I've tried to cut down our sections so they're not terribly long to give you more bite-sized chunks. And the reason I'm doing the second fundamental theorem of calculus first, part 2, is because it gives us a method for evaluating definite integrals quickly, or at least somewhat quickly. Think about it. Thus far, if you want to evaluate a definite integral, you got two options. You have a Riemann sum, a limit of a Riemann sum, which can be very challenging. Can be tedious, not impossible, but can be hard. And then the other alternative is geometry. Now it turns out both of those things don't work most of the time. Using a Riemann sum, especially for a Calc 1 student, does not work out unless you have a very specialized type of function, usually a polynomial. Usually a polynomial. Okay, which obviously we want to work with functions that are not always polynomials. Geometry does not always work unless you have a very specific class of function. Things with it end up using triangles and rectangles and maybe some circles, semicircles here and there. The repertoire of geometry formulas we have is pretty limited. So the second fundamental theorem of calculus, the reason we're going to do that before the first fundamental theorem of calculus is that it allows us, again, a way to work with lots of different types of functions and find net area. Okay, so to evaluate a definite integral. So let's just hop right in. Here is half of the monumental result. This is half of the fundamental theorem of calculus. Okay, so what do we have here? The second fundamental theorem of calculus says if f is a continuous function, okay, so all we need is a continuous function over AB, the closed interval AB, and capital F is an antiderivative of lowercase f over the same interval, then our friend that we call the definite integral of f of x dx from a to b is equal to what? Is equal to capital F of b minus capital F of a. That is curious. Why? It says that all we have to do is take capital F, the antiderivative, evaluate at b, then take capital F, evaluate at a, the antiderivative, evaluate at a, and find the difference. And somehow that is equal to the definite integral from a to b. To me, that is just like the most crazy result ever. That you could take, this is because remember, this left-hand side we've been using either geometry for or a Riemann sum, a limit of a Riemann sum. So the second fundamental theorem of calculus tells us that we can evaluate a definite integral by simply finding the antiderivative, plugging in b, plugging in a, and then taking the difference. It never ceases to amaze me. It's just a crazy result that this happens. And we'll take a look later on at why it's true. We need some more tools in our calculus toolbox before we can look at why it's true. But we'll do that in a future video. And for the time being, let's just take it at its word. Take the fundamental theorem at its word, and let's talk about how to use it. Okay. By the way, what does this necessitate the identification of? To use the second fundamental theorem of calculus, you have to find capital F. That is, you have to be able to find the antiderivative. If you can't find the antiderivative, well, then you can't use the second fundamental theorem of calculus. So this is why we spent a significant amount of time several sections ago talking about how to find antiderivatives of various functions, because we have to be able to find an antiderivative in order to apply the second fundamental theorem of calculus. If you can't find it, well, then you can't use it, because that is how the method works. You find the antiderivative, evaluate at B, evaluate at A, find the difference. And if you can't find an antiderivative for whatever reason, then you're stuck with a Riemann sum, or you're stuck with geometry, because you have to be able to find an antiderivative to apply the part 2 of the fundamental theorem of calculus. I'll oftentimes abbreviate it as FTC2, fundamental theorem of calculus, FTC2 for a second. Okay. By the way, you might recognize why, perhaps why we use the integral sign, for a definite integral and for a indefinite integral, because the definite integral of f of x dx from a to b can be thought of as the antiderivative. And now, but here's some new notation. This new notation simply means evaluated at b, evaluated at a, and then subtracted. So here, I'll write it. This can be thought of, well, I'll write it off the side rather. This notation of capital, let's just say capital F of x, from A to B. What that says is evaluate at A, evaluate at B, or sorry, probably do B first. Evaluate at B, evaluate at A, find the difference. So whenever you'll see me use that notation a lot, and what it means is simply evaluate at B, evaluate at A, and then find the difference. So going back to my point down here, is that you see now perhaps the reason why we use an integral sign in both cases. Because a definite integral from A to B can be found by identifying the antiderivative, or we can call it an indefinite integral, and then evaluating the indefinite integral at B, at A, and then subtracting. So again, here I'll just to stress out what this means is, this is capital F of B minus capital F of A. So capital F is the antiderivative. You plug in B, you plug in A, subtract. Okay? Cool. Now, let us look at an example here. In fact, let's look at an example where we use a Riemann sum and then do the exact same thing with the fundamental theorem. So, I just want to stress to you why the fundamental theorem is so important. Let's get some more space here. Okay, that's probably enough space for us. Here, let's just choose one. I'm going to specifically choose an example that has a trivial solution if you can employ the fundamental theorem of calculus, and has, a routine solution if you want to do a Riemann sum. So let's see. Let's evaluate the definite integral. Let's see here. Let's go from 0 to make it easier. From 0 to let's not go to 0. Let's not make it too easy. Let's go from 1 to 2 of what function? Let's do a quadratic. Let's do let's do this. 3x squared dx. So this will have a trivial solution. It'll take 30 seconds to do. if we apply the fundamental theorem of calculus. But let's show how long it would take to do a Riemann sum. So a Riemann sum, according to the limit definition of the derivative, you have the limit as n goes to infinity of the sum from I equal 1 to n of some appropriate f of c sub I times delta x. Okay, so let's do a couple calculations off the side. What is delta x? Delta x is always b minus a over n. Okay, so what's a? Well, a is 1, that's the lower limit of integration. B is the upper limit of integration, so 2. So delta x is 2 minus 1 over n, so 1 over n. Okay? All right, so that's b minus a over n. Now, what about f of, or what about c sub I? You know, c sub I, that's your endpoints, your left endpoints, right endpoints, midpoints. I'm going to use right endpoints because those are usually easier. And those are given by a plus delta x times I. Okay, so if c sub I, if a is 1, you get 1 plus delta x is 1 over n times I. That's not so bad. And now we can do our Riemann sum, because this is equal to the limit as n goes to infinity, sum I equals 1 to n of f of c sub I. So that means take c sub I and plug it into your function. Well, our function is 3x squared. So 3, 1 plus 1, oh, not I, 1 over n times I squared. That's f of c sub I times delta x. Well, delta x is 1 over n. So that is the appropriate limit that we need to evaluate to find the exact value of this definite integral. Okay, so let's see, equals a limit as n goes to infinity, sum. Oh, you know what? Before we do much, let's factor out the constant. What do we see here? 3 is a constant, and 1 over n is also a constant. Now, why is n a constant? Because it's not indexed I. The only thing that's changing in this summation are I terms, and 1 over n is not an I term. So we can factor out a 3 and a 1 over n. In other words, 3 over n. Now, I'm not going to factor them out of my limit. I suppose I could factor the 3 out of my limit, but I can't factor the n out because the limit obviously is changing with regard to n. Now, what does that leave me with? That leaves me with 1 plus essentially 1 over n times I. Well, that's I over n squared. Okay, now just all to the side here. What is 1 plus I over n squared? Okay, well that's 1 plus I over n times itself. So that's 1 plus, okay, I over n times 1 is I over n. So I over n plus another I over n times 1, or just itself. O plus I squared over n squared. So that gives us 3 terms. If we combine, we get 1 plus we have I over n plus I over n. That's 2I over n if you add those appropriately, plus I squared over n squared. So now I can replace the 1 plus I over n with my 3 new terms, and I get the limit as n goes to infinity, 3 over n times the sum from I equal 1 to n. Now I have 3 terms. I have 1 plus 2I over n plus I squared over n squared. And now, just like we've seen several times now, my immediate next move is to take the sums individually. So to take those summations individually, I still have a 3 over n out front, open some parentheses, sum from I equal 1 to n of 1, plus the sum from I equal 1 to n of 2I over n, plus the sum from I equal 1 to n of I squared over n squared. Okay. Next up, we have some constant multiples we can factor out of the two latter summations. So we have the limit as n goes to infinity of 3 over n. Now that first sum, it's already the sum of a constant. Just leave it alone. Nothing to do there. But notice we have 2I over n. Like I mentioned up at the top, the only thing that's changing in these summations is I. So I can factor out the constant multiple 2 over n times the sum from I equal 1 to n of I. Now, likewise, with this next one, this last summation, I have I squared over n squared. The n squared on the denominator is not changing. I can factor it out. So 1 over n squared times the sum from I equal 1 to n of I squared. Now, at this point, we have that familiar situation where I can simply take the summations, I can resolve the summations using those identities that you should have memorized. I'll give you a little refresher. The sum from I equal 1 to n of c is just c times n, a constant. The sum from I equal 1 to n of I is n times n plus 1 over 2. And lastly, we need I squared. The sum from I equal 1 to n of I squared is n times n plus 1 times 2n plus 1. Oh, that's a little too messy. 2n plus 1 all over 6. Okay, and so this gives us the limit as n goes to infinity, 3 over n. Okay, 1 is a constant. So the sum from I equal 1 to n of 1 is simply 1 times n, or n, plus 2 over n. Now the sum from I equal 1 to n of the i's is n times n plus 1 over 2, plus we have a constant 1 over n squared times the sum of the I squareds from 1 to n, which has an identity, n times n plus 1 times 2n plus 1 over 6. Okay? Now it's just a matter of taking this limit, cleaning it up, and getting to a point where we can recognize, okay, that goes to 0, that goes to 1, this goes to 2, or whatever the case is. So equals the limit. I'm going to clean it up before I distribute that 3 over n. So we have limit n goes to infinity. We have a 3 over n. I'm just going to clean up inside the parentheses a little bit first. So the first term is just an n. Well, that's just an n. Just leave it. There's nothing to simplify there. But the second one, we have a 2 over 2. Those cancel. And an n over n. Those cancel. Well, that leaves me with just n plus 1. So n plus n plus 1. Okay, plus. Now I have n squared I have n squared on the denominator and n on the numerator. So if I cancel off a 1n, that leaves me with on the bottom a 6n. And on the top, I have n plus 1 times 2n plus 1. So if I distribute that, I get, 2n squared plus n plus, that's plus 3n plus 1. Like so. Okay, I can clean up just a little bit more before I distribute. Limit as n goes to infinity. So I have 3 over n. N plus n, that's 2n plus 1. Plus that 2n squared plus 3n plus 1 all over 6n. And now I can distribute my 3. Actually, you know what? I'm going to do two things here. I'm going to factor out a 3 in the limit because that 3 is a constant and we know can come out of a limit. The n, though, is changing with regard to the limit. I'm going to factor that into my other terms. So I'm going to distribute a 1 over n. In other words, divide all my terms by n, and I get 2n over n plus 1 over n plus 2n squared plus 3n plus 1 over 6n squared. And now I can take the limit. So I have a 3 out front. They fixed that weird looking 3. A 3 out front. And now let's take the limit. Notice each of these terms, I can simply observe the degree of the numerator versus the degree of the denominator. With the first term, they're equal. So that goes to a what? A 2. With the second one, the numerator is a constant, and the denominator is a variable. It's going to go to 0 as n goes to infinity. Plus, okay, notice the last fraction, the last quotient, has a degree of 2 on the numerator and denominator. So this goes to 2 over 6 as n goes to infinity. And so I get what? 3 times 2 plus 2 over 6. So 2 over 6 is what? 2 plus a third. 3, okay, a third. If you want to add 2 and a third, would be what? 6 over 3 plus 1 over 3 would be 7 over 3. 3 over 3, yeah, 6 over 3 plus 1 over 3 would be 7 over 3. 7 over 3 times 3 equals 3. So that took significant effort to find via the limit definition of the definite integral. So that is the exact net area. In fact, we can say that's the exact area because what do we know about this region? Well, 3x squared is a parabola that looks kind of like this. Oh, not like that. It's symmetric, so kind of like this. So still not perfect, but I guess close enough. And we want from 1 to 2. So from 1 to 2 is like this region, and that region is at or above the x-axis. So yeah, we could say that is the net area, or the area is 3. Okay? Now, here's the crazy thing. Let's find the exact same answer using the fundamental theorem. Here. Let's show how crazy quicker it's going to be for this particular example. Now, it won't always be quick. Well, it won't always be easy in general, but it's definitely super quick for this example. So what does the fundamental theorem say? Fundamental theorem says if you want the definite integral, we said from 1 to 2 of 3x squared dx, all you have to do is find the antiderivative of 3x squared dx. What's the antiderivative of 3x squared with respect to x? Well, it's x cubed, yeah? That's the antiderivative of 3x squared. Remember, an antiderivative is a function such that when you take its derivative, you get, in this case, 3x squared. So x cubed is an antiderivative. It's not the antiderivative, it's a antiderivative of 3x squared. And then we evaluate at 2 and at 1, and then take the difference. Equals. Okay. This says evaluate at 2, so you get x cubed. Evaluate at 2. Oh, no. Cubing it, not squaring it. 2 cubed minus 1 cubed. 2 cubed being 8. 1 cubed being 1. Equals 7. Oh, what did I do down here? I said that 3 times 7 over 3 was 3. Don't think so. 7, which we confirm using what? 30 seconds of our time? Maybe a little longer since I talked through it. But that is the beauty of the second fundamental theorem of calculus. Now, why was that so easy, the work there in blue? Because we had an easy antiderivative to calculate. So the trade-off is, obviously a Riemann sum takes a lot of time and effort. Okay, and that being the case, I'm going to ask you one question probably on a test about it. Otherwise, I'm going to assume that you're going to be using the fundamental theorem part 2, the work in blue here. Now, the reason that our work in blue was so easy and fast is because we had a very easy antiderivative to calculate. 3x squared dx has a super easy antiderivative. Much of the work when applying the second fundamental theorem of calculus, all of the work basically goes into finding the antiderivative. And of course, there's a little bit of arithmetic afterwards, but that, as long as you're careful, that shouldn't be an issue. But the fundamental theorem necessitates that we find the antiderivative. So if the antiderivative is tough to find, well, then that's where we're going to spend our work. But here, 3x squared had a super easy antiderivative, and so that's why this went so fast. So, second fundamental theorem of calculus is awesome. It allows us to replace a whole page worth of work with, a couple quick lines of work to produce the exact same result. Okay? But, what we'll do in the future is much more interesting examples where the fundamental theorem is not necessarily a walk in the park, but it allows us to work with really weird and interesting functions that we still have to find the antiderivative. Okay, so in the next video, we'll tackle actually next several videos, we'll tackle many examples of applying the fundamental theorem part 2 and how we're going to use that now instead of Riemann sums, instead of a limit of Riemann sum. Because, again, different ways to get the exact same answer. Each one has their place. Both are important. But the fundamental theorem part 2 is going to be our go-to method going forward. It's important to know both, especially for testing purposes. But for routine, definite integral evaluation, the fundamental theorem part 2 is going to be what our go-to method from here on out to the rest of the class. All right, let me know if you have any questions. I'll catch you in the next video.